Hello everyone, this is Wenchen and Xiao from Databricks. Today we will do a deep dive into the new features of Apache Spark 3.1. A bit more about Databricks. We are a data and AI company, and we provide the first lakehouse, which offers a simple platform to unify all of your data, analytic, and AI workloads. We are working with over more than 5,000 customers across the globe, and we have a culture of innovation and dedication to the open source. We have initialized several open source projects in the data space that are quite successful. I'm Wenchen, and both Xiao and me are working for Databricks. We focus on the development of the Spark team in Databricks, and both of us are Spark committers and PMC members. And Spark 3.1 has a lot of features in many areas. In general, every Spark release focuses on three things: readability, stability, and performance. Today, we will highlight some of the new features. Please read the release notes if you want to know all the details. The first topic I'd like to start with is ANSI SQL compliance. Today, ANSI SQL compliance is a major effort of the Spark project. It includes an ANSI mode, which enables a more strict behavior, such as failing the query if the import is invalid. It also includes adding more functions, SQL syntax, and features from the ANSI SQL spec. We hope this can make Spark easier to use for the common SQL workloads and use cases. This is also a long-term effort that the Spark community will keep investing. In ANSI SQL, invalid import is serious, and the query should fail when hitting invalid import to ensure data quality. In the last release, Spark 3.0, we added the runtime overflow check for mass operations and functions. In Spark 3.1, we follow this principle more closely under the ANSI mode. For example, divided by 0 is a signal that your data may have some issues. Without ANSI mode, Spark returns none, which may hide the data issues and produce wrong result to the rest of your data pipeline. And with ANSI mode, Spark now throws runtime exception to capture the data issues. Similarly, many other data tricks have been added to different places, such as if you want to cast a string to an integer, and the string is not a valid number format, then Spark now fails under ANSI mode. And if you want to cast a string to date with a partner string, this will also fail if the string is not in the valid data format. So with ANSI mode, Spark can capture the data issues earlier to ensure your data quality of your pipeline. In addition to runtime checks, the query compiling phase also becomes more strict under ANSI mode. For example, without ANSI mode, Spark can cast an integer to timestamp, and you have no idea what the integer means, number of seconds from epoch or milliseconds. So with ANSI mode, Spark now follows the ANSI SQL spec to define which kind of cast is allowed. And confusing casts like this from int to timestamp is forbidden. This is a screenshot of the ANSI cast doc, and you can find it in the official Spark website. This is an example. If you put an invalid cast in your query, so for better user experience, Spark provides the alternatives in the error message, and you can replace your cast with one of these new functions that have clear semantic. So for example, if your intention is to treat the integer as numbers of seconds from epoch, then you can use the new function timestamp seconds, which has a clear semantic that this is the seconds from epoch, not milli or microseconds. In the upcoming Spark 3.2 release, we plan to create the ANSI mode and complete all the pieces to make it production ready. It includes a new implicit cast behavior under the ANSI mode. In the last slide, I talked about the implicit cast that is specified by the users. Spark also has implicit cast, which asks the cast automatically for your queries. For example, if you want to add an integer with a double, the type is not matched, and Spark will cast the integer to double instead of filling the query. So this makes your life easier for writing SQL queries, but also brings confusions if the cast is not added properly. So in Spark 3.2, we will follow the ANSI SQL spec to define the explicit cast rules to make it more strict and more reasonable. We will also revisit all the functions and operators to add more runtime data checks to ensure the data quality. And sometimes people may know that the data is dirty and just want to get the null result. If the input is invalid, we also will provide some new functions which will not fail during runtimes with invalid input. So for example, we will add a new function try divide, to return none if the divide by 0 happens. Next one is the querytable SQL syntax. A while ago, I did a survey among my friends, and many of them don't know that Spark has two different querytable syntax. The native one uses the using class to specify the data like Predicate and other classes to specify options, partition columns, and so on. Spark also supports the have querytable syntax to attract the have users at the early days, and the have syntax is very different from the native one. This is pretty bad for Spark users, as they have to learn two different syntaxes for create a table. And what's worse, if you are from a traditional database, you don't know this Spark or have syntax and just write create table, it creates a have text format table, which is super slow. In Spark 3.1, we unified these two querytable syntax. Now there's only one syntax, which is compatible with both have and the native one. We also added a config to allow to create packet tables by default if you simply write create table without specifying the data source. Note that this config needs to be set manually, otherwise Spark will still create have tables for backward compatibility reasons. In this release, we also added the proper support for CHAR and VARCHAR type, instead of simply treating them as string type. CHAR VARCHAR is commonly used in other databases because it gives an upper bound of the data size to save storage space and avoid malformed super large input. Now Spark does the length check properly during the data table insertion. You can see from this example that a runtime error happens if the input string exceeds the length limitation of the CHAR VARCHAR. For example, this is try 5, so the input cannot exceed 5 chars. And then the input is A, B, C, D, E, F, which exceeds the length, so it fails. For the char type, Spark also follows the ANSI SQL spec and passes the value to the length of the char type. So look at the example. The column 1 is a char type with length 5, and the length of its value is always 5, even if the inserted value is not 5 lengths. Like for example, we insert ABC into the table, column 1, and whose size is 3. But if you just scan the table later, the length is always 5 because we pad the value during the table insertion. This behavior actually is not very useful and sometimes confusing. It was useful in the very early days of database, but now most of the time you can just pick VARCHAR type. In this release, there are many other ANSI features that I don't have time to go through in details. So for example, in this release, we defined the SQL temple view and permanent view behaviors. Now we always repass and analyze the view SQL string when reading the view for both temple and permanent views. So doing this, we can capture the table data change for the views. Otherwise, for temple view, we just capture the logical plan. Even if your table changes, like add more files or remove some rows, it will not change the view result. So now this consistent between temple and permanent views. We always capture the table data changes. We also support the column list in the insert statement. So now you can put the column name in after the table in your insert into command, and to reload the queries of the import query, so columns of the import query. And we also support the ANSI nested blockade comments in a SQL parser. In the upcoming Spark 3.2 release, there are many other ongoing work for ANSI SQL compliance. So for example, we will add the ANSI year month and data interval data type to replace the current interval type, which is very limited. The current interval type is not comparable because you cannot compare a month and 3 days, as a month can be either less than or equal to or more than 3 days. So it's not make sense to compare a month and 3 days. In the new type, we put months and days into different types. So now we can compare each type individually. We will also add ANSI timestamp without time zone type to simplify the handling of timestamp. And we will also add a new declaration framework for the correlated subquery to support the auto-reference in more places. We will also add a new feature, lateral join, which allows you to reference the columns from the join left side in the join right query. We will also add SQL error code, which is more searchable and cross-language and GPT compatible. Next, I'd like to talk about node decommissioning. This is an important feature in Spark 3.1 to improve stability. Spark engine is fault tolerant. However, recovering from failure has overhead. Node decommissioning is to reduce the failure recovery overhead. It can gracefully handle scheduled SQL shutdown. SQL shutdown is fine to Spark, but it has cost. So first, all the run tasks on the executor are wasted and need to be rescheduled. Second, the RDD cache blocks and shuffle files on the executor are lost and need to be recomputed later. In the real world, there are several cases that the SQL shutdown is known ahead. So for example, Spark has a feature auto-scaling to tune the size of the cluster depending on the demand. And in that case, Spark sometimes can decide to shut down one or more idle executors. If you deploy Spark on cloud, like AWS, there is EC2 spot instance, which will notify the executor being it's going to be killed to make way for other accounts, and this is very cheap instance. And similarly, if you deploy Spark on Google Cloud, there is also GCE preemptible instance, and it has the same feature as above. It is very cheap, but the node can go away at any time. And if you deploy Spark on-prem using YAML or Kubernetes, they will also kill the containers with notification to make way for the higher priority tasks. So you will know that the container or the executor will be killed within a window like 1 minute, and so you can do something to make sure the shutdown will not have very large overhead. Let's see how this feature, node decommissioning, helps this case. So here is a simplified workflow for how it works. So first, there is a shutdown trigger, which can be something in like Spark Autoscaling Manager or cloud vendors. The shutdown trigger will send a signal to executors to notify the shutdown. Next, the executor will do two things at the same time. First, it sends a message to the driver to notify that this executor is being decommissioned. Second, it will start migrating data blocks to other live executors. So in this case, let's say we have two other executors alive in the cluster. So executor 1 will start migrating data to them. Next, the driver gets the message and stops scheduling tasks to executor 1. The data migration may not complete before the executor 1 is shut down, but it's fine. This is just a best effort. As long as there are some data blocks being migrated, we can save recomputing for these blocks. So as a summary, what the node decommissioning do is, first, it migrates data blocks to other nodes before shutdown to avoid recomputing these node blocks later. And second, it stops scheduling tasks on the decommissioning node as they likely cannot complete and waste resource. And third, Spark will launch special tasks for tasks running on the decommissioning node that likely cannot complete to finish the job earlier. So eventually, this feature makes Spark more stable by reducing the overhead of SQL shutdown. So far, we have talked about the usability and stability improvements in Spark 3.1. Next, let's talk about performance improvements in Spark CPU, which is a major focus in every Spark release. The first improvement I'd like to talk about is shuffle hash join. So let's look at how shuffle hash join is done in Spark. For the two tables being joined, we pick the smaller one as the build side. First, we will shuffle both sides, both the tables, to partition by the join keys, so that the same keys appears in the same partition. Next, for each partition, we load all the data of the build side to build a hash table. Then we iterate all the data from the probe side and look up the hash table to find the match. If there's a match, we join these two rows to produce the result. So we can easily see that the sharp hash join is not robust. We don't know how small each build side partition is, and building the hash table may OM. So for example, if the build side table is skilled, there may be a very large partition, and then building the hash table on that side can OM on the executor and crash the application. So as a result, Spark always prefers the summary join over hash join to avoid OM. However, users may still want to turn on the sharp hash join to avoid sorting the join tables. If they know that their table are not skilled and the size is okay, and will fit the memory, so there will not be OAM. However, because Spark never used the sharp hash join by default, and over these years, we only add new features to the thermal join, not sharp hash join. So in this release, we work hard to make sure the sharp hash join is on par with other join algorithms like the thermal join and broadcast hash join. So the work includes we add the code gene for the sharp hash join, and we support more join types in the sharp hash join, and also we handle the unique keys, kind of a fast code path for the sharp hash join, and so on. And after this release, you can safely turn on not safely, but you can turn on sharp hash join if you know the OM will not happen, and it can give you some performance boost. And in the future, we will keep improving the sharp hash join to make it more robust. So first, we will rely on the AQE framework so that we can see that, hey, we know the size of each partition. So if they are small enough, we can safely turn on the sharp hash join. So this can avoid you doing this manually and make wrong decisions. And second, we will also support splitting in the sharp hash join. So even if there is one side being very large and can build the hash table, the join can still be wrong and just slow, but not OM. The second thing I'd like to talk about is partition pruning. This is very critical for file scan performance, as it can reduce the files to scan. So in general, before Spark launches the tasks to read files, it first sends a request to the underlying catalog, like the Havana Stone, with partition predicates to get a list of files to scan. So, and obviously, if Spark sends more partition predicates, the catalog can more likely to prune more files so that you can scan less files and improve the performance a lot. In this release, we did a lot of work to send more partition predicates. So for example, now we support contents, start with, and with in the partition pruning. And now we also support the data type columns in partition pruning, whereas before it only supports very simple types like numeric and string type. We also support not equals and not in predicates in the partition pruning. So this is not a full list, and we will keep expanding this list to push down more predicates to the catalog and get less files to scan. A similar topic is predicate pushdown. In the last slide, I mentioned that Spark can use partition predicates to reduce the number of files to scan to speed up the scan performance. For certain file formats like Predicate, they store the statistics like max-min values of some columns in a file. So Spark can use the Databricks to reduce the data chunks read from the file. So it's also important to push down more predicates into the file scan node. However, predicates cannot always be pushed. So for example, if you have a join node, and the join condition will likely mix with columns from both sides. So for example, if you join T1 with T2, and the condition may be T1.key equals to 1, and T2.key equals to 2. Because this is an AND predict, we can safely push down these two predicts into the both join sides. So for T1, we must say that the key must equal to 1, And for T2, the rows produced by T2 must meet the requirement key equals to 2. However, if we use the O predict to compare these two small predicts with T1, T2 keys, then we can push down, because for semantic of the O, so you cannot have some very strict requirement of both join sides. So similarly, if there is a more complicated predict like this, the third one, as long as the root node is the O predict, then you cannot push down because it's kind of mixed and you cannot push down this predict into both sides. So same problems happens in the normal predicts if they mix with data predicts and partition columns. Because as I mentioned, the partition predicts is handled by the catalog to reduce the files to scan, and the data predicts is handled by the file format to reduce the file chunks from the files. So they are handled by different places, and we must separate this data and the partition columns in the predicts to be able to push it down. However, if we look at the last predict more closely, I mean the third example, there's something we can do. So for all the rows produced by T1, so it either meets the requirement that key equals to 1, or it must meet the requirement key equals to 3. So there's something we can do here to make Spark more smart and push down some predicts into one join side or other places. So it turns out that there is a theory for it, which is called conjunctive normal form. So for a general predict like A1 and A2, O, B1 and B2, so we can rewrite it into a more verbose form, and that combines 4 predicts with AND. Now it's very happy to see AND because now we can split the predicts and push down each part separately. In this release, we use this theory to push down more predicts to reduce the disk I/O in the file scan. At the end, I'd like to talk about one ongoing feature in Spark 3.2. So Spark is famous for running long queries to be a successor of Hadoop. And as a result, over the years, we don't pay much attention on the query compiling latency, as the query compiling time can be ignored comparing to the query execution time. However, we don't want to stop here. We want to attack more use cases, such as short queries, to make Spark a truly general purpose SQL engine. So we are doing a major improvement of the Catalyst framework to speed up most of the analyzer and optimizer rules to cut down the query compiling time to half. And after that, we may see more bottleneck of the query compiling time. And maybe, for example, maybe we will improve the task scheduling time to make Spark faster when scheduling tasks and to make it fit better with short queries. Please stay tuned. Next, my teammate Xiao will take over and introduce the rest of new features in Spark 3.1.
Thank you, Wenchen. I'm Xiao Li. Next, I will introduce the new Spark 3.1 features in streaming, Python, enhancements on usability, documentation, and the environment. And at the same time, we'll also present the feature work in the upcoming releases. Structured streaming is one of the most important components for Apache Spark. Here, I will summarize the major streaming improvements, including a new streaming table API and support for stream join and the multiple monitoring enhancements. At the end, I will also talk about the ongoing work related to the state store. Stretch streaming makes streaming processing much simpler. On Databricks, the usage of streaming is growing very fast. Every day, the number of records processed by our structured streaming is more than 120 trillions. You can easily transform batch processing to stream processing. Streaming sources and sinks can be viewed as unbounded tables. The stream of events can be seen as rows that are appended to an unbounded table. These concepts have been widely discussed in the streaming community. In Spark 3.1 release, we added 2 APIs in DataStream Reader and DataStream Writer. When you want to create or write to a streaming table, you can simply call Spark spark.writestream.toTable without specifying the location. When you want to load a streaming source, you can simply call spark.readstream.table to read it as a streaming job. You just need to specify the streaming table name without location. And of course, you also can read it as a regular tables using spark.read.table. Because this is a data lake table, it will output the current snapshot. A data lake brings ACID exit transactions and simplify your streaming applications. Starting from Spark 2.3, we added the support of stream joins. You can join two streaming data frames in inner, left outer, and right outer join types. This release, we also added two more join types, full outer and left semi. The outer and semi joins have the same guarantees as the inner join regarding watermark delays and whether data will be dropped or not. In Spark 3.0 release, you already can monitor your streaming application in live UI. In this release, you also can review your streaming application metrics after the cluster is shut down. Also, we added two more streaming metrics in both live UI and the Heat server. In scheduled streaming, we process data from streams in batches. However, for some queries, we need to persist information across batches, and this information must be tolerant to any kind of failure. So this information needs to be efficiently acceptable and efficiently persisted into external fault-tolerant storage like S3 or HDFS. Typical stateful streaming operations include stateful aggregations, job duplicates, and the stream join. In Spark 3.1 release, we added 4 metrics of a state store to live UI and the Spark T3 server. It includes aggregated number of total state rows, updated state row, and the state rows dropped by the watermark, and the aggregated state memory used in bytes. And these metrics are useful for monitoring the capacity of the state store. In Spark 3.1, the default state store is HDFS-based p-value stores. When the stateful queries are processing data in Spark workers, the p-value state data is stored in an in-memory hash map. And the state updated are committed as a data file in a state store in the worker. And these data files are periodically collapsed into the snapshot files to improve the recovery efficiency. However, this solution has 2 major drawbacks. The maximum quantity of the managed states is limited by the heap size of the executor. Because these states are maintained in memory. So second, it is slow. When the user enables advanced features like watermarking and the timeouts, it becomes pretty slow because both requires full scan over all the data. In the upcoming Spark 3.2, we'll open source a solution that is being used in Databricks. By default, we are using RocksDB for state store. It can manage state of any size and make all advanced features fast and robust. In this solution, for every partition of every stateful SQL operator, so there's a state store to store that partition's keyed state in every batch. The task that processes a stateful operator's partition will use a state store API to update or remove keys, and then commit a new version of the key values in the store. And the version is the same as a batch ID, and it's used to recover the correct version of state data in case a task or batch needs to be re-executed. Our goal here is to build a state store that stores the binary key values in ROTSDB. And ROTSDB is running inside the executor process. The ROTSDB files on a local disk will be synced to a stable file system on every version commit. On recovery, the necessary file will be copied from the remote file system to the local disk to restore the correct version of data in ROTSDB. Next, let us briefly summarize what we did in the Project Zen. Project Zen was started last summer. It is to improve the Python usability, make PySpark more Pythonic, and improve the error handling. The Python programming language itself becomes one of the most commonly used language in data science. In Databricks, we saw the same trends. In our notebook users, 47% of commands are using Python. It becomes a top one language. Improving the usability of a PySpark is critical to the success of a Spark. Today, I want to emphasize the two major PySpark features in Spark 3.1. Then I will also introduce the ongoing work. We are porting Koalas into PySpark in the upcoming release. So after that, PySpark will have pandas APIs and also provide native visualization and plotting features. Python will remain a dynamically typed language. Although the type is just an annotation in Python, it already can help us in many different ways. The benefits have been widely discussed in the Python community. In this release, we added the type hints to the PySpark. Thanks to this work, PySpark are becoming simpler to use. Most IDE and the notebook can enable auto-completion for PySpark. For example, when you type Spark in Databricks notebook, you can simply press Shift and Tab, and you will see the doc strings of Spark session. That includes an example. When you type Spark context dot, you can press Tab, and then it lists all the valid variables and functions. With these auto-completion features, you do not need to read the API reference document. This greatly improves your productivity. And also, the added type hints help us improve the API reference doc. The doc can automatically generate the input and output types based on the hints. More importantly, it improves the code quality. Type annotation enable IDE or MyPy to detect the errors without running your Python code. In Spark, we already run MyPy in our CI systems to capture the bugs. Because Python is not static typed language, it is easy to write code in Python and make undetected mistake. After we added the type hints, your IDE, like IntelliJ, can check your code and find the common bugs. Here, this shows you are pressing invalid input parameters in your code. So this is highlighted in your IDE. For the new PySpark users, many of them do not know what are the simplest way to manage the Python dependency. It becomes a common question. In this release, we make it simpler and document the solution. The basic idea is to automatically pack the dependency and ship it to the worker nodes and unpack it on the working directory of the executor. It supports all the three popular environments, including Conda, virtual environment, and the PAX. For details, you can read the blog post, how to manage Python dependencies in PySpark. Now, let us discuss ongoing efforts in the community. If you follow our former summit keynotes, you might know the project Koalas very well. So this project was announced 2 years ago. Because pandas does not scale out to big data, Koalas fills a gap by providing pandas equivalent APIs that works on the Apache Spark. We want to unify two ecosystems and provide a seamless transition between small and large data. One of our Koalas customers told us, by changing only 1% of their pandas code, they were able to reduce the execution times by more than 10 times, from a few hours to just a few minutes. In the last 2 years, the growth of Koalas was very fast. Koalas was pre-installed on Databricks. Every month, Koalas is imported more than 2 million times. In open source, based on the PyPy stats, Koalas has around 3 million downloads per month. In the last quarter, Koalas has been used by 84 different countries. It sounds like Koala is now being used in Africa. We need to expand the use base in Africa. After a recent vote by the whole Spark community, the community decided to bring Koalas into Spark. In the upcoming release, all the Spark users can use both Spark API and the Pandas APIs to process your data. This will simplify your migration from Pandas to Spark. And these Pandas APIs also benefit PySpark users because they support many tasks that are difficult to do with PySpark. For example, plotting data directly from the PySpark data. To convert your Pandas code to Koalas, you just need to change your import statement and the patch alias names. It is simple and straightforward. After the change, you can use the Pandas APIs to process and visualize your data. And after porting the Koalas code to PySpark, we changed the package name from Databricks.koalas and to PySpark.pandas, and also the alias name, PS. If you are the existing Koalas users, you need to update the import statements in your existing code to utilize the new version of Koalas in the Spark. Then the new Koalas features will be only added to the PySpark in the future. The last line of this example shows how we visualize the data using plotting API. Most of the Python data science library support plotting features, but it is missing in PySpark. After porting Koalas, PySpark users can easily plot and understand their data visually without converting it to the third-party data structure. This is another example by using the Pandas API on Spark. We can visualize a PySpark data frame by one histogram. We support 2 plotting backends. By default, it is Plotly, but you also can switch to the matplotlib. The Pandas API coverage in plotting capability has reached 90%. In the future, we can add more Spark-specific plotting APIs based on your request, based on our own community request. And welcome your contribution to our Pandas API support, visualization support, and project deck. And we will continue the investment on this direction, make PySpark simple to use for the Python community. Spark 3.1 release and also includes many usability improvements. We are trying to make Spark simple to both beginners and the experienced user. Here, I only highlight 4 features. Conversion between timestamp and Unix time and the conversion from date between the date and the Unix date are pretty useful. Spark 3.1 includes a few utility functions for these conversions. And here are a few examples. You can call timestamp seconds to build a timestamp from the number of seconds from UTC Apple. And you can also call the unit seconds to convert a timestamp constant to the number of seconds since the UTC Apple. Before Spark 3.1 release, we already have a few related utility functions to Unix timestamp and Unix timestamp and from Unix time. So their names are close, but their input and output data type are different. So the existing functions are used for conversion between long values and the timestamp strings. And also, we introduced the two utility functions for getting and setting the current local time zone. Before the release, you can do the same thing by using the SQL configuration spark.sql.session.timezone. And the datetime handling is pretty complicated. I would suggest everyone to read the blog post, a comprehensive look at the dates and the timestamps in Apache Spark 3.0. By the way, in the next release, we'll also add a new data type timestamp without time zone, which is a part of ANSI SQL Compliance. Explain is critical command for performance tuning. It can output the execution plan for your queries. In Spark 3.0, we introduce a new format for explain command, and that is explain formatted. Starting from this release, our Spark UI uses a new format by default. And also in this release, the explain command can also show the runtime plan optimization caused by adaptive query execution in better ways. And in the next release, Apache Spark will turn on the A2E adaptive query execution by default. In Spark 3.0, and more join hints were added. These hints should be used with extreme caution because it is difficult to manage over time. It is sensitive to your workloads. And if your workload patterns are not stable, the hints could even make your query much slower or even room out of memory. When we serve our customers, we found some customers are trying to broadcast a huge table, and they did not realize the table size is much bigger than the original one. To quickly identify whether your hints are properly used, you can rerun the queries by ignoring all the hints. That becomes simple in Spark 3.0. You don't need to change your queries. You just need to set the session-specific SQL configuration spark.sql.optimizer.disable hints to true. And after the value change, the query plan will not be affected by the hints. Then let us talk about the error message. Starting from the last year, the community started working on the error message improvements. And there are three major projects. First, grouping exception message into dedicated files. After that, it will be easier for our developers to audit the new messages and improve the message quality. And the second, we build the error message guideline in the community, and our error message should be standardized and actionable. And the error message should explicitly answer what, why, and how. And we welcome your contribution to improving our error message. In the upcoming release, we are also proposing to add length agnostic and locale agnostic identifiers for the error messages. And after the changes, each error message has its own identifier. And the SQL state are the portable error code that are part of ANSI SQL standard. Here is an example. We are unable to resolve a column from a query because it is missing in the input relation. And in the new proposal, the message has an error ID, SPK 10,000, and a SQL state 42704, which is from SQL standard. And with this message identifier, your application can easily capture the root cause from a long stack trees, and then either report it to the end user directly or automatically track your queries. In Spark 3.1, we also made multiple major updates on the documentation and the environment. I want to introduce our new document for Python users and the search function in our main documentation side. In the past, the major contents of the Spark documentation side were majorly targeting like a Scala SQL users. However, some example code and the description are confusing to Python users. And starting from this release, we introduced a new documentation side for Python users. And in this website, the API reference is richer. And you can search the site based on keywords. And based on our experience in Koala's documentation development, we also introduced a live notebook. Python users can directly play the live notebook to try the features in the latest version of Apache Spark. In addition, we also added the search function in our main Spark documentation side. Finding the result page is becoming much faster. And also, we keep adding the new contents into our SQL reference pages. For example, we added a type conversion into the ANSI compliance page. For Python users from PyPy, you can download the PySpark in different Hadoop versions. The default version in Spark 3.1 is Hadoop 3.2. And you also can choose a prebuilt Hadoop 2.7 version, which is the default in 3.0 or the user-provided version. In Spark 3.1, we dropped the official support of Python 2.7, 3.4, and 3.5. And also the Hive 1.2 distribution is removed from the official release. And the new release is based on the Hive 2.3. If needed, you can also build it by yourself. In Spark 3.2, support for Apache Benzoes as a resource manager is deprecated and will be removed in a future version. And this talk covers the features of Spark 3.1. Due to the lack of time, so there are still many other nice features not being covered by this talk. Please download the Spark 3.1 or try Databricks Runtime 8 for these new features. Now, the community is working on the new features for the next release, like Spark 3.2. There are many exciting features. For example, lateral join support, the new declaration framework, 2 new data types, timestamp without time zone and interval, and also latency reduction in query compiler and scheduler, and also more optimization features are added to improve the performance. And we turn on the adaptive query execution by default in Spark 3.2 release. Many thanks to the Spark contributors over the whole world. Thank you. Thank you, everyone. If you have any question, please feel free to post it. Wenchen and I will answer it. Thank you.